Okay. Good evening, everyone. I was in the situation that I need a new job, and to get a little bit more used to C++17 and so on, I've started to implement a genetic programming library. And on the way to getting the most performance, I've tried some of the 3 implementations which I came up or which I could find on the internet. And I would like to use the chance to present you some of my results, so it's not completely wasted time. So let's talk first about what is genetic programming and which example I choose from the genetic programming domain, and some of the structures, cons and pros, and so on. So my motivation was I just needed something to talk in interviews, which sounds interesting, and machine learning, genetic programming is always a nice topic. So what is genetic programming? It's an optimization strategy which is using some of ideas from the evolution theory, like the fittest individual gets the most new individuals, or the chance is much higher that he is populating the next generation, and ideas like mutation and mixing of genes. So genes can be one way to represent the genes is in tree structures, which is quite useful if you think about that if you take a node and switch it with another individual, and so you get a lot of information from one individual to another individual. And after you get a new generation, you have this fitness function, and this fitness function gives you a score for each individual. And after this run, the best individuals are chosen to making a new population by operations like crossover, where parts of one tree are just swapped to another tree, and this process repeats until it finds the optimal solution, or if it runs into another limit like max generations and so on. So one of the examples which are heavily used or was described in one of the first books which went into genetic programming is the artificial ant problem. It's not so we have here a matrix, and this ant should have the task to find all the sugar cubes on this path, but only with a limited knowledge about the environment. So the ant can only see the the content of the grid in front of them, and the actions which the ant is able to do are, if a sugar cube is in front of you, do the first node. If it's not a sugar cube in front of you, do the second node. These P2 nodes are just nodes which contains 2 other actions. So you would have here a combination of turn right, or move forward. And let's so it's a first step. It would go to the first node and look if a sugar cube is in front of him. Yes, a sugar cube is in front of him. then it would evaluate the first next node. And one of the steps, so for the genetic programming problem, you need to have some limits to decide which ends are the most fittest. So you give him a limit of steps he can do, and you count how many sugar cubes he found. So these are these S and E numbers. In the next evaluation, it would not find a sugar cube in front of it, so it would go to the false branch and just evaluating the false branch. So the end is doing not very intelligent stuff here now, but if you think of generating a branch of random trees with these nodes, some of the ends are a little bit better, some of them are very worse, and so like after 20 generations, you get something which is optimal to find all the sugar cubes. So,
I have a question.
yes.
The sugar cubes on this instance of the problem or on random instances of the problem?
So there is a special description in the book for a special problem, but so this end would be very good in finding on this trail. So you would have to find another fitness function which would test the same end with different trails, and then you would get a more generic end, because this end would be trained only of this. So you have to do a lot of work in this genetic programming. It's not solving these problems by itself. So this would be like the normal procedure where you generate a random population of ants. You would just check the best ants and do the genetic operations in the middle. And after you get a new generation, you would choose and iterate as long as you are not satisfied with the solution. So to measure the fitness of the end, you need some way, like in simulation. The simulation for this problem consists of a class which simulates the board with the sugar cubes, and you can just use the functions to move the end. And after you told the simulation that it was should move this way, and you can at the end read out the score and use the score to make a new generation. So how would we program a tree structure with the classic object-oriented way? So we would first create an interface class, and which has an eval function, would get the simulation, run the needed action on the simulation, and return. So this would be the interface. Then, since we have here nodes, we need a way to tell if node that it has two child nodes. So we would have the second stage of the class, an array with unique pitters. Since we are using object-oriented programming, we have to use heap allocated objects and have to live with the problem that we have unique pitters. And yeah, so this would be the implementation for move. Quite simple. The next implementation for if food is ahead would just use this AND board simulation to ask if food is in front. If it's in front, it would evaluate the first child node and so on. So the problem with this solution is that we have to use a heap allocation from the beginning, unique putters. The nice part about this, you don't have to describe what object-oriented programming is for the people. And one of the disadvantages is if you don't like pointer arithmetic, pointer semantic, and so on, it's maybe a little bit. Maybe you can try find another solution which is more low level without heap allocation and so on. So in C++ 14, a std variant is was included in C++, and std variant has some usage where it can replace object-oriented programming by using the visitor pattern. So we would just, the implementation which we would have a variant, define two behavior tags, and a visitor pattern. And the visitor would get a reference to the simulation, and depending on the variant content, it would just do the needed action. The nice part about this is the user on the user side could implement a lot of different visitors without having you could think about a visitor which prints out the current state of the simulation or other things. And since the visitor is implemented on the user side of the library, it's quite modular. So, but we have a problem. As long as you are, so std variant is has to know how big the types which he has to store are at definition time. And the problem is if you have a tag which has other ends inside, it would generate an infinite size big variant, because and of course we can't use end node here on this side because we didn't have defined end node. So the solution is just to forward declare this if food ahead tag and use this if food ahead tag. But this is also not possible because std variant needs to know the size info on declaration, and it can't know on this part the size of this class. So there is a solution for this, boost recursive wrapper, which just accepts this name and internally stores a pointer to the object which it has to store. And since the pointer is 8 bytes or 4 bytes, boost variant is satisfied with his requirements and can now be created. And then you are able to create this variant structures, recursive variant structures. I'm using here boost and not std variant because of std variant didn't implement it boost recursive wrapper, or because maybe because recursive wrapper has to allocate on this heap. So std variant was, I think the focus was more always allocate on the stack. So boost variant is a little bit more broader in this direction. So, and in this way, we could add to our visitor just one another operate call overloading, and we would be able to call recursive the visitor on our child nodes, and at the end it produces the same results. My experience with it is traversing the variant tree is a little bit problematic, because you have with variant point value semantic, but for traversing the tree you often want to have to return an address to the node which you found, but often you get only a temporal object, and if you return an address to this object, you are ending in segmentation faults and so on. And one of the disadvantages with boost variant is that it uses internal boost preprocessor, and the error messages are not very easy to digest. So the question is, how fast can be this tree traversal or evaluating of this tree? So since I wanted to play more with visitor, I just generated a visitor which produces C++ code. This C++ code is then included in another compilation unit, compiled and evaluated. Of course, this is not changeable by runtime anymore, but it should give us a good expectation what's the minimum runtime of this procedure should be. So the end was first as a generated as a recursive variant. Then the visitor created this C++ code. This C++ code was then included in another unit and compiled. So the nice thing about this, you hopefully get the raw performance from as fast as possible. Oh. And the bad part is, of course, you are getting a dependency to your build system, and you can't change this end anymore if it's compiled C++ code. But it's a maybe interesting experiment for a problem which has to be solved once and run very often, where you look at every possible nanosecond and so on. So instead generating ifs and functions calls, we could also generate some other static types like tuples, and the tuples are filled with these tags, and the decision which action is created is made by this function overloading magic. Sorry. So you would just create this function decides which action is to do by the first tuple arguments, tuple content, and the rest of the tree is hidden in this true branch type and false branch type. And if you so this way you would implement this proc2 node, which has two children, and the nice part about so your AND would be implemented in this way, where you you have to use it all at compile time again, like the C++ generating example, but it's a little bit more contained, and you are still able to iterate over the top tuples with HANA for each or similar compile time constructs. And the nice part about it is it has the same runtime characteristics like this hard-code generated C++ code. And it can be traversed. So can we find another way to implement a tree structure in C++? And so how about function pointer, where you have a function pointer, and this node stores a behavior, if it's a move node, a right node, or left node, or P2 node, and also the possible children. And the nice part about this, these there's no templates here, and no object-oriented programming, virtual functions, and so on. Just this function pointer, which can be changed at runtime. So the user would just have to define an array of different nodes with different behavior. So this would be an if node, and this would be like a move node, and so on. And it's quite flexible because you have one customization point where you can define different nodes. And it's very low boiler code, and that C++ code is also very easy transferable to C code. So function pointers and so on. And you have value semantic for these examples. So, okay, the next tree would be why at the end generating trees. Instead of generating a tree from a serialized string, you could just use the string, and depending on the string and where we are currently with our cursor in the string R, change our behavior. So this would be a representation of the end tree, and we know that the if node has two children, so this would be the true case children, and this would be the false case children. And this P node has two children, so this would be the first children. This has also, two children, so you can jump in this string with a cursor, similar to like a tree, and you save the part where you have to generate the tree. Traversing is a little bit slower because if you want from here skip some parts, you have still go to this part and look how many children here are, and then you could jump to this. This example is not very good in this direction, but traversing is a little bit slower. Later on, there are some benchmarks, and so let's talk about benchmarks. I've compared GCC 8.2 and Clang 7, and which compiler generates the smallest binary, and GCC was in average 50% smaller than Clang. This can this strongly depends on the end, and so it's can vary if you change the node or if you have another end simulation. If it's for the speed test with -03, in average, Clang was 13% faster. One outliner was the implicit tree implementation, where Clang was 30% faster than GCC. So maybe it's interesting to look what Clang has done in this code, because it's not so much code, so you could theoretically find out what magic is done by Clang. Yeah. So to compare the runtime characteristics, I've used the object-oriented programming example as a base. This is my 100%, and the static code, which was generated and compiled and then run, was 1/3 of the runtime of the object-oriented programming code. So the boost variant was slower than the object-oriented programming code. The function pointer implementation was the same, like in comparison to object-oriented programming, and the implicit tree was 6 times slower. Okay. Any questions? Yes.
Genetic programming is all about mutating the tree and finding a tree that fits best.
Yes.
In the example you've given, you demonstration trees. You didn't show any mutation of those trees. How did you, or did you consider how to mutate?
The problem is no one pushed me to have a finished result, so I've lost track in benchmarking different tree structures, and so boost my first idea was to replace object-oriented with boost variant, because variant is new and cool, and everyone wants to know what variant can do for our code base. So that's why I focused quite on boost variant, and it's quite messy, because as you saw, the visitor pattern uses recursion, and you need to return somehow and reference to the current node. So you can take the best one and the second best one individual, and choose one of the nodes in this tree and swap them. And if you are using this visitor pattern, you are running very often in this problem that you're getting temporal objects, and if you're returning an address of this object, you are running in segmentation faults. I never had so many segmentation faults like with experimenting with this direction. But of course, you have value semantics, so you should maybe forget to get an address of this node. Just copy the node to somewhere else outside, but it didn't feel very effective, because you walk once the tree with recursion and find a node which is suitable. You giving the value outside of this visitor pattern. Then you walk the second individual, and put this new node on the new position, and it gets the old node also somewhere outside, and then you would run again on this first individual, and put the swap operation would take like 3 steps, where you have traversed the tree 3 times. When you would have some references which are safe to use in this tree, you would save quite some time. So I didn't go further in boost variant. I now will go probably with the function pointer implementation, because the boilerplate code is quite small, and as you saw, the performance is similar to the object-oriented programming solution. And yes, any other question?
Which data did you benchmark here? Was it always the same tree?
Yeah. Yes, it was. I've run this the complete genetic programming simulation before, where I would get one optimal end, which is able to solve this complete puzzle in one in the given time and given restriction. And so this end has like 14 nodes. It's always all the code and all the nodes are on GitHub. So I could so it makes a quite difference if you take an optimal end, which solves this problem in easy going, and if you choose if you random generate a tree which has like 100 nodes, and you would get very different runtimes. So I would take the benchmark results with a lot of salt, or no, I don't know how do you call it. It very depends on where the how the board is laid out, and if the end is optimal or not optimal, and so on. So don't take this for sure.
Is there a reason why you didn't choose array-based tree, where actually the left child is on for the index I will be 2 multiplied e, and the right child will be on 2 multiplied e plus 1 in the array?
Just time constriction.
So everything will be allocated on the stack, because it's array-based, and it would like to be very efficient to implement trees.
Yes, so one of the things is this end example is often used as a benchmark for genetic programming. So I couldn't change the nodes which I have. So some of the nodes don't have any children. So I would have to introduce a nope node which does nothing, or where I would have the tree. So my next idea is, instead of the implicit tree idea, was to use the string and just have a cursor moving on the string, and then choosing which behavior should the end now produce. But maybe it would be more efficient to have an array and fill the array with already the function pointers to the behaviors, and then run over the function pointer behavior array. so it's just a time constraint. So maybe if I have enough time, I will add this node, implicit array node somewhere. Yeah. Any more questions? Then, thank you for your time. Thank you for having me.
Thank you all for coming. I don't know if any pizza left, but if wants, you're welcome. I don't know if Pablo, after next meetup is